And welcome to the practice problems video on line integrals. Okay, so number one, we're going to, let's see, they give us the following vector field of y squared comma x squared. Okay, so pretty simple. We're working with two dimensions here. Alright, so we're also given that our curve is the following. The y equals x to the negative 1 graph. For x is between 1 and 2, and it is oriented from left to right, okay? And they also give us in the problem a parameterization already for this, which is just going to be t, comma, t to the negative 1. Okay, so the first, so this is all of our given, okay? And part A, there is a part A and a part B. Part A says to calculate f of c of t, okay, and ds arrow, or also known as t ds, okay? Alright, so in this problem we're just basically like breaking every step down, so it makes it easier for when you go to solve a problem all the way through by yourself. So calculate f of c of t. Alright, so first of all, c of t, as they gave us, is given by t comma t to the negative 1. So that would be t comma t to the negative 1, where t is our x of t, and t to the negative 1 is our y of t. That's like little functions within the parameterization. Okay, so what f of c of t would be is then we're going to plug in t to the negative 1 wherever we see a y. So that would be t to the negative 1 squared, comma, and then we have to plug in a t for wherever we see an x. So that would be t squared. Okay, so this is just going to give us t to the negative 2, comma, t squared. Alright, so that is our f of c of t. Okay, so that's the first part, and then the t ds, that is our c prime of t dt. Okay, so in doing this, we have to find the first derivative. So that would be, so first derivative of the first thing with respect to t is just going to be a 1. And then the first derivative of t to the negative 1 is a negative t to the negative 2. Alright, and then we have a dt sitting at the end here. Okay, so make note of these two things, and we'll be using them in the next part, B. So part B tells us now we have to find the following. We're going to find f of c of t dot the c prime of t dt that we just found, and we're going to evaluate, basically put everything together. So we're going to evaluate the entire vector line integral f dot t ds, or you might know this as f dot ds arrow. Okay, so here we're just gonna, this is in the last slide we found that this is t to the negative 2 comma t squared, and this is going to be dotted with our c prime of t dt, which we found was 1 comma negative t to the negative 2 dt. So this is the first part here. So when we dot this, we basically just multiply the first components, so that'll be 1 times t to the negative 2, and then plus a t squared times negative t to the negative 2, and then all of this times dt. So this is going to equal t to the negative 2 minus a t squared minus 2 dt. So that equals all of this times dt, a t to the negative 2 minus a 1 dt. Okay, so that was the first part. And now that we have that, we're just going to evaluate the line integral. So that would simply be, and this is as t goes from 1 to 2. I should write that. So t, which took the x spot, is going from 1 to 2. So this will be from 1 to 2 of this thing, right? That's how you would normally set up a line integral. So I'll just set it up like that right now. And then I'll plug it in the next step. Okay, so now what we can do is just plug this in, as we found from previous steps, into here. So we just get t to the negative 2 minus 1 dt. Okay, so when we integrate this, we get a t to the negative 1, then we have to have a negative sign in front, minus another t, as t goes from 1 up to 2. Okay, so when we plug everything in, we get negative 1 over 2 minus 2 minus negative 1 over 1 minus a 1. Okay, so this is a negative 2, and then it becomes positive with the negative outside. So this is a negative 1/2, okay, negative 1/2 minus a 2 plus a 2. So these ones cancel there, and we are left with a negative 1/2. Okay, so that is the line integral all the way through for this problem. Okay, so number 2, second example, is we're going to find, again, working with line integrals here, vector line integrals. So we're going to find this, which, again, you might know as this, with the little arrow over the s. And our given vector field for this problem is x squared, comma, xy. Okay, and then our curve, so our curve is going to be part of circle, given by the formula x squared plus y squared equals 9. And so the part of the circle is restricted with, or by, x is less than or equal to 0 and y is greater than or equal than 0. And it's oriented clockwise. Okay, so this is all of our given, and let's try to make sense of it. So first of all, let's look at our curve, okay? So it says it's part of the circle, x squared plus y squared equals 9. So that's the equation for a circle when your radius equals 3, okay? And also it says that x has to be less than 0 and y is greater than 0. So that implies that we are in quadrant 2, okay? So that's the top left corner, right? So we have something that looks like this. Here's our x and here's our y. And we go 3 in each direction. 1, 2, 3. And this is our curve right here. Okay? So this top left corner of the circle. So this is negative 3 and this is 3. And it also says that we are oriented clockwise, so we're going this way, right? Remember, with vector line integrals, not scalar line integrals, but vector line integrals, when you're dealing with those, the direction matters, okay? So here's our start and here's our end point, okay? And now we have to parameterize this curve. So this is one of those examples where they don't give you an explicit c of t equals blah, 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 but we have to figure it out ourselves. So in general, the parameterization for a circle is going to be the r cosine theta, or r cosine t, I guess, comma r sine t, okay? So we have r, which is 3, cosine t, comma r, which is 3, sine t, okay? And you see, if we stop here, what we would actually get, so this is the parameterization for a circle of radius 3, but starting at 0 and going this way. Okay? But what we're doing here is actually starting on the other side and going in this way. So what we have to do, as you can see, if you go from both directions, we'll have it going, the y is going to be increasing, right? If you were to come from this way, it'd be increasing. So sine is good, basically, because it's going up all the way to 1. At the top here, but the cosine, that would be our x values, we actually start on the negative side. So our first, if we were to plug in a 0 per se, we would get positive 3, but what we want is a negative 3 to start off. So we want to put a negative in front here. So as far as parameterizations go, you can kind of get creative with them. So yeah, if you are a creative person, or even if you're not, this is a great way to work on your creativity and cleverness. So anyways, so that is that. And so t is going to go from, let's see, what should the bounds for t be? They're going to be from 0, right? Because if we plug in a 0, we'll get negative 3, 0. So that's good. And then all the way to the top, so that would be at pi over 2. Okay? So that's that. And then what else do we need to know? We can plug in our c of t into f. Okay, so where this is our x of t and this is our y of t. Okay, so looking at f, we're going to plug in negative 3 cosine t wherever we see an x. So we're going to do negative 3 cosine t squared, comma, and then again negative 3 cosine t times y, which is 3 sine t, parenthesis, and then an arrow. Okay, and then simplifying here, we get 9 times cosine squared t, comma, negative 9 cosine t sine t. Alright, so this is our f of c of t. That's one part. And then on the next slide, I'll continue to find the c prime of t. C prime of t is going to be a negative 3 sine t and a negative 3 cosine t. Okay, so we have all of the parts that we need to plug it into our formula, which is from a to b, as t goes from a to b, of f of c of t dotted with c prime of t dt. Okay, so this is going to be from 0 to pi over 2, because those are the bounds for t. And then we got the following: 9 cosine squared t, comma, negative 9 cosine t sine t, dotted with what we just found, which is negative 3 sine t, comma, negative 3 cosine t dt. Alright, so let's dot this out and we'll find what it is. So multiplying the first components are negative 27 cosine squared t sine t, and then we have a plus 27 cosine squared t sine t. So this is actually looking pretty good, right? So what we have is a 27 times something minus 27 of that same something. So this is going to be 0. Therefore, the entire line integral, given the curve, the parameterized curve, and the vector field that we were working with, we got 0. Okay? Alright, now on to the last problem. So number 3, what this one is, we're computing the line integral, well, we're computing the following integral. I'll just word it that way. So, of y dx minus x dy. Okay? So, also the curve they give us is y equals x squared for x is in between 0 and 2. Alright? So, this is what we're given, and we have to compute this integral here. So, looking at, let's look at the curve first. So, to parameterize this curve, what you do is you make one of the variables, traditionally x, equal t. So, x equals t, and therefore y has to equal t squared, if you plug that in, right? So, t and t squared, okay? And then t will go from 0 to 2 because it takes on the same values as x, okay? We just replaced it with a variable, basically. So then c prime of t, lots of t's going on, that's just going to be 1 comma 2t, all right? Okay, so what this is actually our dx dt is the 1, and 2t is our dy dt, right? Because the t here was x of t, and here t squared was y of t, all right? So you see that, and then what we actually have, now let's look at the integral. So what we have is an a to b, and then y times dx dt minus x times dy dt, and everything times dt. See how I went backwards a little bit? I just added in the dt's again, because if you add them in here on the bottom to each term, you have to add one on the outside, over here, on the top, like over 1, right? Okay, so here I just went backwards a step, and then what I'm going to do now is this is our a, and this is our b, because they are the bounds for t. So we're going to be going from 0 to 2, and then for our y, we're going to plug in whatever our parameterized y was, so that would be t squared, okay? And then dx dt, which we found was 1, so times 1, minus x, our parameterized x is now t, and dy dt is 2t. Alright, so let me figure out the parentheses here. I think I'm good. Okay, so now we just integrate like normal. Well, we're going to simplify first. So we get t squared minus a 2t squared times dt. So that just equals integral from 0 to 2 of negative t squared dt, okay? And then when we integrate here, we get a negative t to the third with a 1 over 3 in front, as t goes from 0 up to 2, alright? So then this is 1 over 3 times 2 to the third minus 0, which equals a negative 8 over 3. Alright, so that's how you solve that kind of problem. So again, this was just like an example of one of the problems given to you in a different form, right? So we kind of had to work with it a little bit, and then we got it into a more understandable and workable form. Okay? Alright, so that does it for this video, and I'll talk to you later if you watch future videos.